Good evening, everyone, and welcome to our talk. It's the last talk of the day, so hopefully it will be interesting enough for you to all stay awake till the party after this one. So my name is Misquitta. I'm Principal Consultant at GraphAware, and today we're going to talk about knowledge graphs and relevant search using Elasticsearch. This is really based on one of our live customers that we did this for. Presenting with me today is Dr. Alessandro Negro, our Chief Scientist, and he'll take over for the later part of the talk. So today we're going to cover the rise of knowledge graphs, the application in relevant search. We're also going to talk about specifically knowledge graphs in the e-commerce domain, because this was really our customer case, infrastructure, and then combined search approaches. So first, knowledge graphs. So the Forrester Wave for master data management said that knowledge graphs provide contextual windows into master data domains and the links between domains. And this is really important because there's been, over the last few years, very huge leaps from data to information to knowledge, and then finally automated reasoning. And what's key about knowledge graphs is that they play this fundamental role because they gather data from a variety of data sources and they link them together in mostly a very organic form. So you're also able to grow it, query it easily, maintain it easily, and yet keep it very relevant and up to date. You heard in the morning's keynote from Emil that knowledge graphs have really been on the rise for the last couple of years. And we're only going to talk about a few examples in this before we dive into e-commerce. So in e-commerce, of course, you have multiple data sources. This is one of the primary use cases for knowledge graphs. Category hierarchies, typically you never have a single hierarchy of products. You have the same products that actually form part of various different hierarchies. And this is quite a difficult problem to address if you don't have a graph. And finally, you have the combination of not only products, categories, data sources, but they're also influenced by marketing. When you're out to sell something, you don't sell it just on the basis of having a product, but there are always marketing strategies and promotions that influence what you sell. So the combination of all these three really merge well into the concept of a knowledge graph. Enterprise networks as well have for a long time been trying to connect the individuals in their network, so partners, customers, employees, opportunities, providers together. And knowledge graphs helps you discover relationships between all these connected data, and therefore you can discover new opportunities. Finance, the textual corpora such as financial documents, these contain a wealth of knowledge, and you will have seen many case studies, specifically the Panama Papers, which actually link together a lot of such types of documents. And what you end up with is a very structured graph of entities and how these are connected. Health is a very, very important use case for knowledge graphs, and this has actually had many, many practical use cases over the last few years because it unifies your structured and your unstructured data from multiple data sources. And it integrates these into a graph-based model with very dynamic ontologies, okay, where data is categorized and organized around people, places, events. And this enables you to generate a lot of knowledge around based on the co-occurrence of relationships and data. And so really patterns in disease progression, causal relations involving disease symptoms, okay, and the treatment paths for all these diseases. New relationships have been discovered that were previously unrecognized before, okay, simply by putting all this data together and applying a context around where this happened, who was involved, other natural events that might have happened around this data. And finally, criminal investigation and intelligence have had very many papers published recently about how knowledge graphs have really helped them to investigate cases. One of the most familiar cases has been around the area of human trafficking, and knowledge graphs have helped because this is a very vague field to track, and a lot of the information is very obfuscated. So you have coded messages posted on public forums which form a pattern, and here's where tools and techniques such as NLP come into the picture to really decode these coded messages, make sense of them, apply context around them. And another very key part of the whole knowledge graph is that, especially with law enforcement, you really need to have traceability from your knowledge graph back to your source of information. Otherwise, none of this would hold up in a court of law. So with a knowledge graph, you also maintain the traceability of your data from source, okay, to the point at which it really provides you the information or the evidence that you need. So now we're going to switch a bit to some of the problems you see around data sparsity. When you talk about collaborative filtering, one of the classic problems is your cold start. You cannot really recommend products or things to other people if you do not even have other people in your graph or other purchases in your graph. And this is commonly solved through things like tagging based systems or trust networks. And Alessandro will later talk about knowledge graphs and how it helps solve all these problems. If you don't have collaborative filtering, even content based recommendation suffers a lot of problems due to missing data or wrong data. If you don't have an enhanced graph to pull all this data together, these are very hard problems to solve. Text search as well, with sparse data, you end up with very user agnostic searches, and the world is moving away from anonymous agnostic searches to very relevant context oriented searches. Similarly, relevant search is a problem. So these are some of the areas that we'll touch upon in the later part of the presentation. But really, knowledge graphs are what we used to know as knowledge bases, but on steroids. They provide you an entity-centric view of your linked data. They're self-descriptive because the data that's described is really described in your graph, and therefore you're capable of growing this data in a very organic fashion, enhancing it as you discover more and more facts about your data, and really you have an ontology that can be extended or revised, and it supports continuously running data pipelines. So it's not a static system that's once built, remains that way forever. It grows as your domain expands. And the last point is that, again, tracing back to the law enforcement cases, it provides your traceability into the provenance of data. And this is very important in many, many industries. So a knowledge graph is really a convergence of data from a variety of places. Of course, you have a lot of your actual data sources, which could come from all over the place in all sorts of formats. You have external sources to enrich the data you have. You have user interaction. So as users play with your application or your domain, you learn more, you feed it back into the knowledge graph, and therefore you improve your knowledge graph. And then you have tools such as machine learning processes or NLP, which really in the end help you achieve your business goals. So I'm going to hand over to Alessandro now, and he will cover the rest of the material.
Thanks, Luan. So let's make this presentation a little bit more practical by considering a specific application of knowledge graphs, a specific use case that is implementing an advanced search engine that delivers relevant search capabilities to their end user. Relevance here is the practice of improving search results, satisfying their information needs in the context of a very specific user experience, while combining our balancing our ranking impacts on business needs. I'll walk you through an implementation that combines graphs, and more in detail knowledge graphs, with Elasticsearch in order to deliver services to the end user. And you will see a real architecture and a concrete infrastructure where combining them both, it's possible to deliver a high-level set of services to the end user. And you will notice how the knowledge graphs could help in this direction, not only because they can solve the issues related to data sparsity that Luan was talking before, but also because the graph represents the right model for delivering this type of services to the end user. So, accordingly to the definition stated before, relevance moves along 4 different dimensions, resolve around 4 different elements that are text, user, context, and business goal. First of all, a search has to satisfy an information need that is expressed by the user using the textual query. So in this context, informational retrieval and natural language processing are key to provide search results that mostly satisfy the user intent expressed by the search query. But relevant search moves toward a more user-centric perspective of the search. That means that we can't deliver the same result set to the same user, even if they perform the same query. So in this way, user modeling and the recommendation engine could help to customize the result set accordingly to the user profile or the user preferences. While on the other hand, context expresses the special conditions under which that specific search has been performed. So context information like location, time, or even the weather could be helpful to further refine the search results accordingly to the needs of the user while he is performing the query. Last but not least, the business goals drive the entire implementation because a search exists only to satisfy a specific need of an organization in terms of revenue or in terms of a specific goal that she would like to achieve. Moreover, a relevant search has to store a lot of other information related to search histories or, for example, feedback loops. And all this data has to be accessed in a way in which they shouldn't affect the user experience in terms of performance. That could mean response time or the quality of the results. So far so good. So here is where knowledge graphs come in, because we will see how knowledge graphs represent the right approach in terms of information structure for providing a relevant search. Because in order to provide a relevant search, a search architecture has to handle an high quantity of data that are heterogeneous in terms of schemas, in terms of sources, in terms of volume, and even in terms of rate of generation. Furthermore, they have to be accessed as a unified data source. That means that they have to be normalized and accessed as a unified schema structure that satisfy all the informational and navigational requirements of a relevant search that we saw before. So more in detail, graphs are, and we will see how, are the right representation for all the issues related to the relevant search that are information extractions, recommendation engines, context representation, and even rule engine for representing business goal. More in detail, information extraction attempts to make the semantic structure in the text explicit. Because generally we refer to the text as unstructured data, but they have a lot of structure related to the grammar, related to the constraint of the language. So you can extract this information using natural language processing, and then you will find that from a document you can extract the sentences, and for each sentence you can extract the list of tags, and then the relationships between these tags based on type dependency, on mentions, on whatever else. So this is a connected set of data that can be easily stored in the graph. And once you store this data, you can easily extend the knowledge that you have about this data, ingesting information coming from other knowledge graphs, like CONVERGENCE 5, for example, that is an ontology structure that can be easily integrated in this basic set of information, just adding new relationships in the graph. On the other side, the recommendation engines can be built using user item interactions that can be easily stored in a graph as a bipartite graph, for example, but also can be built using content-based approach in which you need to use again information extraction or in general, a description or a list of features of the element that you would like to recommend. In both cases, the output of the process could be a list of similarities that can be easily stored in a graph, just as new relationships between items, for example, or between users, and then use them to provide a recommendation to the user that combines both approach, for example. Context, by definition, is a multidimensional representation of a status or an event. Mainly, it is a multidimensional array. It is a tensor. And a tensor can be easily represented in a graph where you have an element that is one node and all the other indexes that refer to that element that are other nodes that point to that specific node. In this way, you can easily perform any sort of operation on the tensor that could be slicing, for example, or whatever else. And you can even easier add new indexes to this tensor, just adding a new node and a new node pointing it to the element. Finally, in order to apply a specific business goal, you have to implement a sort of rule engine. And even in this case, a graph could help you not only to store the rule itself, but also to enforce the rule in your system. So I have to be fair because I promised you that this will have been a very practical presentation. So let's move further and consider a specific use case that is a search engine for an e-commerce site. Because any search application has its own requirements. Let's say has its own dramatically specific set of constraints in terms of expectation from the search. That means, for example, that in the case of a web search engine, you have a lot of documents, and that are pages, obviously, and these documents are completely different one from each other, and even the source of this knowledge cannot be trusted. On the other side, when you think about an e-commerce site, you can think that, okay, this could be simpler. This is not true at all, because it's true that the set of documents is more controlled and is even in terms of number is reduced. But in an e-commerce site, the catalog navigation and let's say the text search are the main salespeople of the e-commerce site, because it is not a way for just searching for something. It's also a way for promoting something, for shortening the path between the need and the buy. So they are very important. So in terms of expectation, a search in an e-commerce site has a lot of things to do. But even more, in this case, you can gather data coming from multiple data sources. That could be sellers, that could be content providers, that could be marketing people that would like to push any sort of marketing strategy or marketing campaign in the system, like promotion, offers, or whatever else. And also, you have to consider the user, so you have to store user-item interaction, or even more store user feedback in order to customize the results provided to the user according to their history in some way. And obviously, again, business constraint. So let's see an example of this is a simplified example of a knowledge graph for an e-commerce site. And we will notice how obviously the main element in this case are represented by the products. Here we have just 3 different products: an iPhone, a cover for the iPhone, and an earphone. So for every single product, we have some information like the list of features that describe that specific product. But obviously, this list of features could change accordingly to the type of the product. So it will be different for a TV or for, I don't know, a pair of shoes and so on and so forth. And starting from this information, you can easily, process, for example, the textual description and extract the list of tags. As we said before, we are talking about information extraction in this case. And once you have the tags, you can, for example, ingest data from ConstantNet 5 and know that a smartphone is a personal device. and we will see how this is available information later on when you would like to provide a relevant search. But apart from the data that are, let's say, common for this type of application, you can also analyze your data and create new relationships between items, for example. So this is how relationships like usually both together jump on. And also you can even manually add relationship, like the relationship between a cover and the related phone. So in this way, you are, augmenting the amount of knowledge that you have step by step, and use all this knowledge during the search, during the catalog navigation. So with all these ideas in mind, we designed this infrastructure for one of our customers, where you can see how the knowledge graph is, the core, is the main source of truth of this infrastructure. And we have several data sources that just feed this knowledge graph, and we have a machine learning platform that just processes this graph continuously and extract insight from the knowledge graph, and then again store this insight in the knowledge graph back. And there is also another part that we will discuss furthermore later, that is the integration with Elasticsearch that allow us to export multiple views with multiple scopes in Elasticsearch, so that we can avoid the front end to impact too much on the knowledge graph, but just use the Elasticsearch as a sort of cache, but also as a sort of a powerful search engine on top of our knowledge graph. More in detail, let's say how we designed the data flow, because we created this sort of asynchronous data ingestion process where we have the multiple data sources just pushing their data in multiple queues, and then a microservice infrastructure that just react to these events, process them, and store these sort of data that are intermediate data in a one queue that then is processed by a single Neo4j writer element that just read this data and store this data in the graph. And this is why we would like to avoid any issue in terms of concurrency. But also in this way we can easily implement a sort of a priority-based mechanism that allow us to assign different priorities to the element that we would like to store in the knowledge graph. And finally, in order to store multiple views in the Elasticsearch, we created this event-based notification system that is highly customizable, and that you can customize in a way in which you can just push several types of events, and then the Elasticsearch writer just react to this event, read data from the knowledge graph, and just create new documents or update existing documents in Elasticsearch. So it's clear how, the Neo4j is the core of this infrastructure, because it stores the knowledge graph that is, as I said before, the only source of truth. There is no other data somewhere else. All the data that we would like to process are here. They converge here in this knowledge graph. And so Neo4j is a valuable tool because allow you to store several types of data, users, products, detail about products, or whatever else, and also provide an easy to query mechanism, an easy to navigate system for easily accessing to this data. More than that, in the early stage of the advanced search process, the relevant search implementation, it can help the relevance engineer in order to identify the most interesting feature in the relevant in the knowledge graph that will be useful for the implementation of the related search in the system. Moreover, once all the data are in the graph, they go through a process of of extension of that mostly comprises three different operations that are cleaning, existing data augmentation, and also the data merging, because you can imagine that you can have multiple sources, so they can express the same concept in different ways. So data merging is also important. But let's say that some of these operations, some of this process can be accomplished in Neo4j itself with some plugins or with some Cypher queries. Other need to be externalized because they are heavy in terms of computational needs, in terms of memory. So we created this machine learning platform that thanks to the Neo4j Spark connector allow us to extract data from Neo4j, process them using the natural language processing or even recommendation model building, and then store, as I said before again, new data in Neo4j that will be useful later on for providing some advanced feature to this relevance search. So here I would like to say that we are trying to use the right tool for the right job, because we can use Neo4j for storing the knowledge graph, and maybe it is the most valuable tool for doing this. But obviously in terms of textual search could be an issue if you would like to perform more advanced textual search on Neo4j. So we added Elasticsearch on top of Neo4j in order to provide this fast, reliable and easy to tune textual search. So as I said before, we again stores multiple views of the same dataset in Elasticsearch for solving several scopes, obviously, for serving several functionalities that are faceting, for example. That means any sort of aggregation of the result set and that you can have. You can serve product details page, or you can provide product variance aggregation. Moreover, you can also provide easily with Elasticsearch auto-completion or suggestion. But it's worth noting here that it is not a database, and we don't want to use it as a database. So again, I would like to stress on the fact that it is just a search engine that, gather in this case data from Neo4j and provide the most valuable tool for textual search in this case. So let's see now how we can use Elasticsearch for providing a relevant search on top of the knowledge graph that we have just built using the infrastructure that I described before. So in this context, I shall define a simple concept, that is the signal. A signal in terms of relevance search is any component of a relevance scoring calculation corresponding to a meaningful and a measurable information. I can say, to simplify, that is just a field in a document in Elasticsearch. But obviously, the most complicated part is how you design this field, you put inside this field, and how you can extract from the knowledge graph and store it in the Elasticsearch that really matter. Because when you think about relevancy, you have two main techniques for controlling relevancy. The first one is signal modeling. That is how, I said, this is how you design the list of fields that compose your documents in order to react to some textual query. And the other one is the ranking function, or the ranking functions, that are mainly let's say, how you compose several signals and assign to each of them a specific weight in order to obtain the final score, and then the rank of the results that you will have. This is not a simple task because you have always to balance between, let's say, the precision and recall, where in this context, precision is, let's say, the percentage of document in the result set that are relevant, while recall is the percentage of relevant document in the result set. It's complicated, but to simplify, we can say that in the worst case, if you would like to return back to the user all the documents, you will have a recall that is 100%, but because you have all the relevant document in the result set. But in terms of precision, you will have a very, very small precision. And even in this case, you can have multiple sources in terms of data, in this case, from the knowledge graph that you can use for modeling your signal. And let me give you a couple of examples, because we would like to, to explore outside of the usual approach to the search. Otherwise, we cannot call it a relevant search. And in this sense, the first approach is the personalization search, the personalized search. And this is, one of the directions that we discussed before about the relevant search. Here, the idea is that we would like to use users as a new source of information, because we would like to provide a customized result set. We would like to customize the result set accordingly to the user profile or the user preferences. So here we have two different approaches. The first one is what we can call profile-based approach, where we create a sort of user profile that could be created manually by the user, just asking him to fill a form, or automatically inferring the user preferences from past searches. And the other approach is behavioral based. In this case, is more related to a sort of recommendation engine that just analyze user item interaction in order to, make explicit the relationship among users and the items. So, and once you have the user profile or the, behavioral information, you have to type this information in the query. And you can do this in three different ways. At query time, that means mainly changing the query accordingly to the recommendation that you would like to do, or index time, that means changing the documents accordingly to the recommendation that you would like to do. Obviously, the third one is a combined approach. Let me give you an example. If you would like to customize the results accordingly to the user and would like to do it at query time, you have to change your query specifying the list of products that the user could be interested in. And in this way, you can easily boost the results if, for some reason, in the result set there is some of the products that the user could be interested in. On the other side, at index time means that you have to store the list of users that could be interested to every single product. And then again, you can easily boost accordingly to that specific matching in that case. So another interesting extension of the classical search is the concept search. In this case, we are moving from searching for string to searching for things, because the user could use different words for expressing the same concept, and this could be an issue with the classical text search environment, where you have to match the specific word that appear in the text. So using the techniques that we described before in terms of data enrichment, you can easily extend the knowledge that you have about every single word, and then you can easily store them in Elasticsearch and react to the query of the user, even if it is not writing the right terms that is present in the specific text. So even here we have different approaches that I try to summarize in this way, because the most basic one is just to add new fields where you can manually or even automatically add the list of tags that could be helpful in terms of describing the content. Or you can write the list of synonyms. So for example, for TV, you can have other synonyms like T.V. or television or whatever else. And in this way, even if in the text you have TV, you can easily react to, and so provide results if the user write for television, for example. Obviously, there is a more advanced approach in this case, in which you can use machine learning tools for augmenting, the knowledge. So in this case, you can use a simple co-occurrence, as well as you can use a latent direct allocation. That means, clusterize your document set and define the set of words that could better describe that specific cluster, and so far the entire documents in that cluster. So finally, I would like to show you two different approaches that we used along the way in this sort of path of integrating Neo4j and Elasticsearch. On the left side, we represented the first approach that we had, in which mostly we have two different elements that are the documents in the Elasticsearch and the graph database. So in that case, when a user performs the query, the query goes through two different phases. The first one is the classical textual search query that is performed 100% on Elasticsearch. And then the first basic result set is, is manipulated, accessing to the graph and then boosting the documents or boosting the results accordingly to whatever rule you would like to have. This could work, but in terms of performance, could suffer a little bit when you have to do complex boosting operation. So we moved to a second approach in which there is more, connection between Elasticsearch and the knowledge graph in this case, because we can see, and this is exactly what we discussed in this presentation, that the knowledge graph is used for exporting multiple views in Elasticsearch. So part of the work is done at index time. And then when the user performs the query itself goes through a first stage that is an enrichment. So accessing the graph, we can change the query, and then we will perform the query against Elasticsearch. And this appears to be a more performant approach, because this operation itself is not related to every single element, but is based on the context or on the user or on whatever else. So it is very fast. And then we can use, let's say, Elasticsearch for what is supposed to be, just textual search. But at that point, we already have a very complex query that is, created using the graph. And even the index are already changed accordingly to the graph structure. So, to wrap up, we can say that the knowledge graphs are a very important buzzword, let's say. Because, we are using graphs for representing complex knowledge. And more than that, we are using a model. We are storing them using an easy-to-query model that allows us easily to gather data from several sources. That means that we can store users, item interaction, we can store whatever else we want. And we can even further extend importing data later on or changing our knowledge graph, adding new information. And on top of this, we can develop a search engine capability using a search engine like Elasticsearch that provide a fast, reliable, and easy to tune textual search engine, and that also provide a lot of other interesting features like faceting or auto-completion. So it is combining them that you can achieve, that you can deliver high-level set of services to the end user. So what is the takeaway of this presentation? That the idea is that you should use the right tool for the right job. In this case, you can use the graph for representing complex knowledge, and then use a simple tool like Elasticsearch to provide textual search capability, advanced search capability to the end user. That's all. Thanks.